Specifying reward functions is hard. Because of this, there has been a lot of interest in reinforcement learning from human feedback. Unfortunately, human feedback is often expensive to obtain. Because of this, we might want to explore other sources of information about human preferences. Let's say you observe this environment. Simply by seeing the vase sitting on the table, you can infer that people acting in the environment have a preference for it being there. And to infer this, you don't need any additional human supervision. Here's an abstract version of the situation. There's a robot acting in a room with a breakable vase, and the human Alice asks the robot to go to the purple door, but she doesn't specify whether breaking the vase is bad. The robot can then learn something about Alice's preferences simply by imagining how she must have acted in the past. So if Alice had wanted to break the vase, then she would have probably done so already. If she didn't care about the vase, then she probably still would have broken the vase just to act more efficiently. Only if she wants the vase to be intact does she go around it and it stays intact. Since we observe, in fact, that the vase is not broken, Alice must have wanted it to be intact. Prior work introduced an algorithm to codify such reasoning, however it's limited to small tabular environments, such as the grid world here. Our goal is to scale this idea to complex high-dimensional tasks where we cannot enumerate the state space, let alone past trajectories. For example, consider this cheetah, which is balancing on the front leg. Intuitively, the cheetah must have followed a trajectory similar to this one to get to this balancing state. In this work, we present Deep RLSP, an algorithm that can do this kind of qualitative reasoning and learn to imitate what must have happened to reach a specific state. The main question we have to address for scaling up this idea is how can we determine what must have happened without full knowledge of the environment dynamics. Here our key idea is to simulate likely past trajectories. So prior work uses knowledge of the environment dynamics and enumerates all possible past trajectories in order to determine what must have happened. In contrast, Deep RLSP learns a model of the inverse dynamics and uses it to simulate past trajectories. To infer preferences from an initial state S0, we use gradient ascent to maximize the likelihood of S0 given a reward parameter theta. Intuitively, we compute this gradient in 3 steps. First, we simulate trajectories backward in time from S0 to determine what must have happened before. Then we simulate forward from the last state of these backward trajectories to determine what our current policy does. Finally, we compute the difference between the backward and forward trajectories, which gives us a gradient that changes the reward parameter theta in order to ensure that the current policy explains what must have happened before S0. So let's take a look at the models we need to be able to compute this gradient. We need a feature encoder and decoder to learn the feature function. We need a policy and an environment simulator to sample forward trajectories. And we need an inverse policy and inverse dynamics model to simulate backward trajectories. Ultimately, we will use all of these models to update our reward. As an input, we get an observed state S0 and a dataset of random rollers in the environment. We use this dataset to initialize several models. We learn the feature encoder and decoder using representation learning, and we learn the inverse dynamics model using supervised learning. Also, we create and initialize a replay buffer from this dataset. Then we enter our main training loop. In each step, we first simulate trajectories backwards from S0 using the inverse policy and inverse dynamics model. From the resulting past state, we then simulate forward trajectories using the policy and the environment simulator. We then compute the gradient on the previous slide and use it to update the reward. The trajectories from which we computed the gradient we then use to update the replay buffer. Finally, we update the policy for the new reward using the soft actor critic algorithm and update the inverse policy using supervised learning. We repeat this training loop until the gradient magnitudes are reasonably small, which indicates that the backward and forward trajectories are consistent. In our paper, we demonstrate Deep RLSP in the MuJoCo simulator. For each experiment, we start with a policy performing a skill such as balancing on the front leg. Then we sample a single state or a small number of states from this policy, and we give it as an input to Deep RLSP. The algorithm returns a reward function and a policy that imitates the original skill. We show that this algorithm can learn common locomotion tasks and other skills in MuJoCo from just a single state. We compare it to an imitation learning baseline and perform several ablations of this algorithm. If you're interested to learn more, come visit our poster, check out the paper and this website on which we provide videos of our experiments.